So first of all, let's talk about wire antennas and the currents on these antennas. And I want to motivate this by hearkening back to your understanding of the currents on a transmission line, a simple two-wire transmission line that is open-circuited at the end. So we have some source driving this, doesn't really matter where it is. That source will produce voltage waves and associated current waves on this wire. And the total current, because this is an open circuit at the end, has got to be 0. As a result of that, for an incident voltage and current wave, there will be a reflected voltage and current wave. The sum of these two voltage and current waves will give us currents that are 0 here and 0 every half wavelength. What we have, in other words, is a standing wave of current on the line. We have to, because there is no possibility for the current to sneak off the ends of these wires. Just parenthetically, the voltage will be a maxima at this end here, it'll be a minima here, it'll be a maximum here, etc. So the standing wave of current is something that is naturally set up on any transmission line that happens to be open-circuited. Let's now look at this transmission line from the standpoint of me taking these two conductors and peeling them apart. What we form when we do that is what we call a linear dipole. It's linear because the wires are along a line. It's a dipole because we have two equal and opposite current excitations, one up here and one down there. And what happens is we still have an open circuit. You can still think of this as a transmission line that is open circuited. So there'll be a null in the current here, but there will also still be standing waves of current along that line. And depending upon where you took that line and peeled it apart to, that'll determine just how many standing wave maxima you have on this set of wires. For example, if I construct this antenna, this linear dipole, from two wires that are each a quarter wavelength long, in other words, the total length is lambda over 2, or half a wavelength, and what I get is a null in the current over here. I go 1/4 wavelength away, that is down to the base where I'm feeding the antenna, and I have a maximum in the current. Over here I have a null, I go 1/4 wavelength away and I have a maximum in the current. But notice the directions of the current. Let me go back for a couple of slides. Notice here that if I have any current flowing on one conductor, there must be an equal and opposite current flowing on the other conductor. When I take these wires and peel them apart, what I'll then have is currents that flow in the same direction in space. Even though relative to the wire end they flow in opposite directions, from a standpoint of which direction they flow in space now, because I peeled these wires apart, they are flowing in the same direction. And so the current standing wave on this antenna is null here, it's positive, but it's also positive right over here at this driving feed point, and then it drops back down to 0 again. That's the standing wave pattern of current on a half wavelength dipole. Now, I can look at various other lengths of dipoles. This is a dipole that's a little bit longer than a half wavelength, but less than 1 wavelength. And what I'll have here is a standing wave of current. It'll have a peak, then it'll start to go down again. What I'll have here then is a driving current, call it I in, which is the current at the input of these antenna terminals, that is less than the peak value of the current on the wire. We'll see how that shows up later in the lecture in terms of being able to interpret the radiation resistance of this device. And similarly, if I peel off longer segments of wire, my length being greater than lambda but less than 3 lambda over 2, what I'll have is, of course, a 0 at the end, a maximum, a null, and then another maximum or partial maximum depending upon just how long the antenna is. For example, if this was a 3 lambda over 2 antenna, then I would have another maximum here at the driving terminals. Now you can also see that the directions of the current along these wires reverse depending upon which maxima you're in. If you're in this first maxima, these currents are in the plus z direction, if you want to call it that, in other words, upwards. And in this segment of the lower portion of the dipole, we also have currents that are pointed in the plus z direction, but these currents reverse in the next standing wave portion, and they're oppositely directed. Now that will have a big impact on the radiation pattern. Whenever you have currents reversing as such, these currents will tend to radiate, and these currents will then null out the contributions of those currents to some extent. How much? All depends upon what the integral comes out to be. So we'll have to work out the radiation integrals and determine exactly how much as we go along. So this is kind of a summary. These are the current distributions along the length of a linear wire antenna. For the case of 1/2 a wavelength, we have the solid curve. Lambda, the dotted curve, 3 lambda over 2, etc., 2 lambda. Finally, get to 2 lambda, in which we have our 2 full cycles. And you can almost figure out just what the radiation pattern of this is going to be. Let me just emphasize this particular current distribution. Let's think about that one a little bit. We'll see this played out in the mathematics as we go ahead in the other slides, but let's ask ourselves, what would be the radiation pattern of this antenna with the current distribution that I drew in red if the observer was off in the XY plane, in other words, broadside to that antenna? Well, any radiation that this observer receives from currents over here are going to be canceled by radiation it receives from currents over there. So you can see already that this series of maxima will have an impact on where what we call the nulls in the radiation pattern are placed. This antenna will indeed exhibit a null off in the so-called broadside direction. In other words, if you want to call it the XY plane, or in other words, perpendicular to the wire. We'll see how that is played out in the mathematics as we go ahead, though. Question?
I didn't understand what cancels.
This current over here, this current filament here, which is pointed positive, will have its counterpart over here.
You can't see what you're pointing at.
Oh, I'm sorry. Is that better?
Yes.
Okay. This current filament here is going to have a counterpart over there, which will be pointed in the opposite direction. It will be the opposite sign, opposite SIGN. And so as a result, the radiation from those two filaments will cancel. And for every other little filament you find here, there'll be also one of equal and opposite extent, and so there'll be cancellation of the total radiation field in the XY plane. Make sense? Okay, sorry about that. Raise your hand next time again if the pointer disappears. Well, now let's get into the mathematics. We can only talk about this from a heuristic standpoint so long, and to really become engineers about the way we use antennas, design them, we've got to look into the mathematics of radiation from wires. What I'm going to do here is postulate now a current distribution on this antenna, and we'll call it I sub E, the excitation current. It's a real current. It's not a magnetic current. It's an electric current, so it's a real measurable current. This is its complex phasor form. And if we take this transmission line analogy, where we peel apart the transmission line ends and then form the dipole, we can state that our current is going to be in the z direction. It's going to have some peak value of I naught, and it'll go as the sine of k times L over 2 minus z prime. And z prime in this case ranges from 0 to L over 2. Down below, the other half of the dipole, this will go as az I naught sine of k L over 2 plus z prime.